All right. Good evening, everybody. I'll be presenting some CFD simulation results for a half-car simulation. So, yeah, project overview. We're going to be looking at the fluid analysis around an open-wheeled style race car. And so the goal was to assist the design of the race car you see here, and also for my aerodynamics capstone. And so the ultimate goal in doing this analysis is to decrease lap time. So by increasing the tire grip on the road surface via downforce production. So different parts of the car, like the wing, will generate downforce. And so that increased normal force on the tires will allow us to take corners at a faster velocity. So there was some conceptual design that went into this about like what aerodynamics components should be considered for analysis. So there was a projected weight distribution of a car to be 70-30 front bias, which is very bad for a rear wheel drive vehicle, because ideally you'd have the majority of your weight over your rear wheels to increase your tractive wheel normal force. And so added front mass and downforce to the front of the car is really unwanted. So we scrapped the idea of putting a front wing on the car and are focusing our design efforts on a rear wing and underbody kit to produce that downforce. So that's what the analysis will cover. Yeah, so there's a pretty basic like experimental design process. So you design a part in SolidWorks, set it up with like a simulation mock, which is like a mock car, so and a driver and stuff. Throw that into CFD, refine your mesh, run the simulation, and then the results I'm getting out are like downforce, drag, and surface pressure distributions. And so that will be iterated to change the geometry of the parts until we have a final design that produces an increase in downforce compared to the original design. There's going to be sets of 3 simulations that are going to be run with each version of the component designs. So this presentation just has results for that first run of the base designs of the rear wing and underbody kit. So yeah, so the configurations are going to be 1 with the car with the rear wing only, B, the car with the undertray only, and then C, the car with both the rear wing and undertray. So this is like an idea of what these components look like. The rear wing was designed last year by in this class and as well as a capstone group. So we're going to be updating their design and evaluating it again with the current car. And then the undertray is something that's being completely designed ground up this year, which is another analysis project in this group, in this class by Brendan Lyons. So there are some of the flow domain boundaries. So we have our little race car in our wind tunnel, and our test velocity is 16 meters per second, which is about 35 miles an hour. And that's like the median vehicle speed determined by a lap simulation model that was completed last year. But you can also just Google average FSAE race car speed, and it's about 35 miles an hour. So that was confirmed by our lap simulator. Yeah, so there's a couple symmetry boundaries, inlet, outlet, a ground condition, and then rotating tires at 668 RPM, which is the 16 meters per second for their radius. So there's a couple things to set up for that rotating tire physics. So there's a couple new coordinate systems. So that was a fun exercise within StarCCM. And as well as the moving ground condition, because the car is not stationary with the air, the car is actually like pushing through the air, and so the air and the ground are moving past the vehicle. The mesh, the final mesh looks like that top image, and there's a couple mesh controls that were applied. So some specifically on the aerodynamic surfaces, and then some in the control volume and in the wake area, to get a better look at vortice shedding or other behaviors like that. And another key area of that mesh was the distance between the ground and the car body, because any increase in downforce due to ground effect, which is essentially just the Venturi effect, is going to be determined by the quality of that mesh. So we have pretty good prism layers, and then at least 3 cells that are continuous through that area. So that'll produce some good results. So the convergence criteria, so the simulation was set to stop when the drag coefficient exhibits asymptotic behavior. And so most of them were converging around 100 iterations at first. And then once I refined the mesh further, they were converging around 200. So this residual plot is for the car with the undertray and the rear wing in that geometric configuration. And although they didn't get down to like, 1 times 10 to the negative 4th, if I let the simulation run to like 1,000 iterations, they just kept climbing down with little to no change in the fields. So as far as the continuity, I felt like this was a good criteria to stop the simulation at. So here are some results of that simulation. So this is a centerline pressure comparison. So along that split line through the car. So run 1A has just the car with the rear wing, 1B has just the car with the undertray, and 1C has both the undertray and rear wing. And so exactly as you'd expect, there's a huge low pressure zone underneath the rear wing, which is generating the downforce, which we expect. So it's just an upside down airplane wing. So instead of creating lift, it creates downforce. And the same thing for the underbody. It is a very subtle airfoil profile to it. And that is generating some downforce, albeit much less than the rear wing. And in the combined model, it's visible that both of the elements are working together. So you can see that when comparing run 1A to run C, there's a new low pressure zone underneath the vehicle, which is what we are trying to create. So here is some nice visualizations of the base case. So that's the run without any aerodynamic devices, and what that flow field kind of looks like. And so you can see some of those streamlines are twisting around those rotating tires. And it's a pretty turbulent area in between the tires. So putting aerodynamic devices in that region isn't going to lead to a lot of downforce production, because the air velocity is already slowed down. And because it's turbulent, you're going to have you're not going to have very good flow attachment to surfaces. So you're just going to be adding weight with your component potentially. Here's a nice visual of the rear with just the rear wing. And it's really cool to see that those streamlines totally get pulled up from the bottom of the car into that low pressure zone underneath the rear wing and in the wake of the car. So the streamlines are only starting at the bottom front of the vehicle. So all those streamlines that are visualized in the back are the end paths of those same particles. And that makes sense. There's a low pressure zone, so the faster, higher pressure air is going to, or sorry, the slower, higher pressure air is going to want to fill that void, and it just sucks right up to that low pressure zone. And then, checking out that velocity field. The velocity field is matching right up with the pressure field. So the higher velocities are underneath the wing, right where that low pressure zone is. Some commentary everybody was giving me was, oh, we need a strong face shield because our driver is just getting blasted in the face by that that high pressure air. And so here's a nice shot with just the undertray, and the car is rotated a little bit in this shot, so you can kind of see some of those streamlines attaching themselves to the curved profile. So in between the tires, as I said before, it's a pretty turbulent area, and so there's not a lot of flow attachment on that flat plate, but there's two streamlines which are very clearly visible, which follow that contour. And so if we are able to improve this geometry and get more streamlines to attach, that will ultimately increase our downforce production in that area. And so the velocity vectors on this one are very similar to the base case without any aerodynamic elements. But there's a slight increase in velocity under the car due to the structure, the undertray. And so here's the run, which is pretty cool. It's both of them. So it's that combined case. And so it's improved on both of the cases that just have one element, and these two parts working together lead to an increase in overall downforce. So that was all the pretty pictures, and here's some numerical results from all of these simulations. So the things that I was tracking was a drag coefficient, frontal area, downforce production, drag, and then the mesh size. And so the drag coefficient and frontal area were good monitors to make sure that the simulation wasn't doing anything super weird. And as you'd expect, as you add more components, the drag increases. And so as does area, and as does the drag force. And then for configuration C, which has both the undertray and the rear wing, we get the greatest downforce production, so 207 newtons. So that's about 4.4, so maybe 50 pounds, maybe a little less, like 40 pounds of downforce. But that's just on half of the car, because this is just a half car simulation. So 80 pounds of increased downforce on like a 725 pound car is pretty significant. And considering you're not adding that same amount of mass to the car. Yeah, that was that's kind of the results. And where do we go from that is if you look at the downforce produced by configuration B, which contains only the undertray, the version 1 of the undertray, it produces 19 newtons of downforce, which is nothing. So improvements on that airfoil profile will hopefully lead to similar downforce production to what the front wing would have provided, which is about 200 newtons of downforce for the entire device. So because we scrapped the front wing from the package, we'd like to produce a similar amount of downforce using the undertray, which is the component we're currently designing. Yes, so some suggestions for design would be reducing the frontal area of the rear wing in order to reduce drag. So going back to the numerical results, the drag on the rear wing was 108 newtons for just half of it. So that's quite a large amount of drag force. And so if we can reduce the area, we can directly influence that drag force. So one suggestion would be to remove that third element. So if you go back to here, you can see that there's 3 airfoil profiles that make up that rear wing. And so that third element has a very small low pressure zone underneath it. And so potentially removing that to reduce manufacturing complexity, reduce weight, and maybe not significantly change the downforce production would be something to look into for version 2 of this design. But definitely keeping the gurney flap, which is the very slight tip that's on that last airfoil profile. So that really keeps this high pressure concentrated on all the top sides of the wing surfaces, and is a good design addition. So yeah, if we can reduce that frontal area, we can reduce the drag on the rear wing. And if we reduce the size of the end plates on the sides, left and right, for mass reduction. So going back to this, if you look at the pressure zone on the rear wing, towards the bottom, there really is not a large low pressure zone. So we could definitely trim some of this material out where there's a negligible pressure difference. And we can also experiment for the undertray. This is experiment with the angle of attack of the airfoil profile to generate greater downforce. And so that's what Brendan Lyon's project is kind of focusing on, is the geometry of that part. And then potentially we could add more airfoil profiles above the undertray to generate more downforce. And for those, we would probably just use the same airfoil profile as a Selig 1336 profile that the rear wing uses, because we have a pretty extensive analysis of that from the previous capstone project. And so an implementation of that might look like the car here from Stuttgart's car, where they have airfoil profiles. They have 3 of them there on top of their side pod structure. However, ours would be closer in towards the cockpit of the car rather than in between the wheels, because that's already a high turbulent, low velocity zone. So the amount of downforce you can produce in that area is pretty negligible. Yeah, and so some improvements to the simulation analysis would be finding the center of pressure location. And that will kind of suggest handling characteristics. So the center of pressure is, well, exactly, that's kind of like the center of gravity, but for the pressure distribution across the vehicle. And depending on its location, the car can produce oversteer or understeer during race situations when there is a lot of downforce being produced. So along like straightaways and, in our case, well, whenever the vehicle is moving, you're going to get a force. But the faster you go, the greater pressure distribution will be, the greater that center of pressure location will have an effect on your handling. And so because our vehicle has understeer as this suspension is currently designed, then we would want to position the center of pressure in a place that could counteract that. Because ideally we'd have kind of a neutral steer vehicle. Another thing would be a cross-sectional view through the undertray profile so that we can look more at the flow right in that area to inform design of the undertray component. Yeah. So overall, that is my report, and I appreciate you all paying attention to it and listening.
Nice job, Oliver. I had a question for you.
Yeah.
How are you calculating downforce?
I'm using the force, let's see, what is it called? Force report.
Oh, I remember when you and Gerry went over that in class. So I guess what I was wondering, and I know nothing about this. It's super interesting, but why would you care about downforce more than the lower pressure underneath the areas of concern, like underneath the car? It would seem to me if you're designing an undertray, you would want to concentrate on lowering the pressure as much as possible rather than looking at downforce specific. I mean, mostly.
I guess they're directly correlated, right? So the pressure distribution between the top and the bottom of the under tray surfaces is what generates that downforce. And so if we can get a low pressure, the best low pressure zone that we can underneath the car, then we will likely be generating a higher downforce.
Yeah, makes sense to me. The other thing I thought was interesting is looking at this picture. You could tell your driver basically how far to stay away from the car in front of them until they're ready to pass, because otherwise they're going to hit some dirty air.
Totally. Right.
That was, you really give them a little heads up. Not that they didn't know that, but it's interesting to see what the air is doing behind the car.
Yeah, it's super cool. And so the distance of the actually, yeah, I should have included like a really nice like full side view, because the wake settles out after about like 2 car lengths behind the car. It's fairly streamlined again.
Really interesting. Thanks for presenting this.
Yeah, thank you for your feedback.
Yeah, I'm not a race car driver, but there's also the benefit of the pressure behind the vehicle. So in this upper right corner plot, there's lower pressure behind the vehicle. So you actually get, if you're drafting in a bicycle, or if you're really driving dangerously behind a semi on highway speeds, like right on the end of a semi, you actually get pushed along because the airflow way behind has a higher pressure, and the airflow in front between you and the vehicle in front has a lower pressure. So you actually get a little boost, but that takes dangerous driving skills.
So if you position yourself like within that that low pressure zone behind the car, because then you wouldn't have that force coming at you from the
exactly. That's what the Peloton is all about. Yeah.
That's what the F1 drivers are always, give me a toe, right? Mm-hmm. They get right up behind their partner.
Yeah, like inches. Yeah. So yeah. So I mean, there's a trade-off. The dirty air is there, yes, but if you can get inside that bubble.
Yeah, unfortunately, these cars don't ever race side by side due to I don't know, safety. But but that could happen, but maybe just not at competition, right? That happens in the parking lot. So,
okay, any other questions?
I was wondering, how does the undertray interact with the wing? It looked like if you add up the downforce for just the wing and just the undertray, and then you look at the combination, that's a bigger number than just the sum of the parts.
Yeah, I noticed that when I was putting these numbers in last night, and I haven't done an analysis of that, but that's a very keen observation. Yeah. Right. There's nothing that I have like any monitors or plots to inform that. If you have a suggestion of maybe what I could look at in this model to.
I thought you were saying there was a low pressure zone in one of these that wasn't present in either of the other two.
I guess what I think I was saying that when I was comparing the pressure scenes between the 3 variations, and I was kind of saying that this run C is kind of just a summation of A and B, because now there's like the presence of this lower pressure zone underneath the car, whereas it was non-existent without the undertray.
Okay, that makes sense. I guess I misunderstood when you were on this slide.
Yeah. I probably didn't explain that too well, but yeah, you're right. There's there's another 10, 15 pound or newtons that are added.
Well, thank you, Oliver, and nice job.